Hello, dear listeners. Today I'm really glad to announce that we have a talk from Professor Dr. Boli, who is an assistant professor in the Department of Computer Science at the University of Illinois at Champaign. She is a recipient of the IJCA Computer Science Thought Award, Alfred P. Sloan Research Fellowship, and multiple any other awards. Also research awards from tech companies such as Amazon, Meta, Google, Intel, IBM, and eBay, and best paper awards at several top machine learning and security conferences. Her research focuses on both theoretical and practical aspects of trustworthy machine learning, which is at the intersection of machine learning, security, privacy, and game theory. She has designed several scalable frameworks for certifiably robust learning and privacy-preserving data publishing. Her work has been featured by several major publications and media outlets, including Nature, Wired, Fortune, and New York Times. So, please start, Professor.
Yeah. Okay. Thank you everyone for coming to the talk, and thank you for the invitation. So yeah, our group works a lot on a lot of things, and today I mentioned that we are really interested in the certified robustness, which is one of the main focus of our group. So it's a great pleasure. I will introduce some of our recent work on certifiably robust learning via knowledge-enabled logical reasoning, and I will first introduce the framework, and we can look into several pipelines, and one major application we are doing is actually autonomous vehicles. So it will be very interesting to look at the potential way of the combination of such a pipeline. So just as a quick start, I think I don't need to emphasize too much about how machine learning is ubiquitous, including autonomous vehicles, recent famous ChatGPT, GPT-4, and the face recognition systems, all kinds of applications in our daily life. But we know that over the years, there are a lot of accidents caused by autonomous vehicles as well. And the output of large model or foundation models could be biased, could leak sensitive private information. And the real world systems such as Amazon Echo have been attacked as well. And similarly for the face recognition systems, a lot of attacks have been constructed, which lead to severe consequences such as misarrest. So although we have witnessed lots of breakthroughs of machine learning AI, especially the last week, I think everyone is super excited. But still, I would say it's very challenging to build up trustworthy machine learning system, even with our powerful GPT-4 and all those advances. We can see still safety, AI alignment, all those the types of angles are still almost open for everyone. And people say we still trying very hard to improve the safety itself. And there are even reporting that projecting that 2023 would be a security nightmare due to the malicious AI. And it is very important to enable such trustworthy machine learning or AI platform for large infrastructures, including power grid network, water networks, and transportation networks, etc. So actually, just the last year, the White House has taken the agenda and published the blueprint for AI Bills of Rights, and emphasizing the 5 important problems, including robustness, fairness, privacy, explanation, and human in the loop. So before we dig into the concrete solutions, we can take a brief look at what's the fundamental problems or causal reasoning behind these problems. So for example, we know that in traditional machine learning, we usually assume the training and testing data are drawn from similar, even the same distributions, right? So that we can train on one and make inference on the other. But in practice, either the training distribution can be manipulated, leading to potential poisoning attacks, backdoor attacks, etc., or the testing data distribution can be manipulated, leading to evasion attacks, maybe some of you have seen, and natural distribution drift, generalization problems, basically. And such a distribution trustworthiness gap potentially will lead to the problems or trustworthiness problems we mentioned before. So based on this, our group mainly focused on designing the robust, private, and generalizable machine learning paradigm for real-world applications with guarantees. That means with a central goal of closing the trustworthiness gap, as we've seen before. And I believe this is one of the actually fundamental goal of different aspect of trustworthy machine learning itself. For instance, from the robustness perspective, we are dealing with either the training or the testing data distribution drift, and start from threat model exploration and the certified defense against them, and leverage knowledge to defend against the potential unknown attacks. And from the privacy perspective, we are trying to minimize the distribution distance of the output to protect the sensitive information of the training input. And from the generalization perspective, we're exactly trying to deal with the natural distribution drift compared with the adversarial distribution manipulation in the robustness case, right? And not only the individual perspectives here, but also we focus on uncovering the underlying connections among those individual pillars here. For instance, we can prove that the certified robustness can be represented as a function of epsilon delta for epsilon delta differential private model, or like under mild conditions, the robustness and generalization can be bidirectional indicators for each other. So with all this, we can build up a holistic view of trustworthy machine learning itself. And today I will mainly focus on robustness, and if we have other interest about different topics, we can discuss offline. So in terms of robustness, we mainly focus on the 3 layers here. For example, from the threat model exploration, this is one example here. Not only like the adversarial examples you have seen before where you can add noise to an image with more L2 norm, but also that different semantic transformations. For example, here, if a car in a rotation and then at certain angles, the LiDAR will fail to detect the car itself, which is a real-world attack. And to defend such attacks, we have been focused on provide a certified defense against such attacks based on data and model properties, which is purely data-driven types of approach, which I will introduce later. For instance, here, we hope that given a sensor fusion model, we can say, given certain semantic transformation, for example, car rotation, like along the z-axis, like 10 degree, and you will certify the lower bound of the MLU of the detection is always lower bounded by some value. So this is purely data-driven approaches, and lots of current research are focused on this. But later on, I want to show that this types of approach has reached a bottleneck in terms of robustness, and we do need some new paradigm shift, which is a recent exploration we are doing for certified defense will knowledge enable logical reasoning to integrate logical reasoning into the purely data-driven models. And we will see what that means, and this talk will mainly focus on this 3rd layer. And let's take a look at the each layer as the quick introduction. So first of all, we definitely want to know, take a step back and define what is robustness and why we need robustness or even certified robustness, and whether existing certified robustness approach enough or not. Right? And yeah, let me know if you have question at any time. So in terms of robustness, there are different types of angles we can look at it. From the autonomous driving perspective, we can see several years ago, our group have developed this first physical attack against the road signs, like the stop sign, which has been exhibited in the Science Museum of London currently and become one of the prominent collections. And we can see that even such just a simple, like a white and black rectangle can fool the models, like the perception model directly, which is quite dangerous. And in the dynamic environment, we can see that indeed, if we drive a car towards the left hand, which is attacked, and right hand side is a control experiment. And by looking at the captions, we can see even in the dynamic environment, the road sign, the adversary road sign will fool the cameras completely. And we have shown these types of attack can be generalized to LiDAR, to multi-sensor fusion system in practice very easily, unfortunately. And not only against the autonomous driving, but also medical domain. Like for example, on the right-hand side, if you add a small noise to the medical data, the segmentation can be completely missed. And of course, NLP, large foundation models, if you change even just a single word a bit, your semantics prediction will be completely flipped. So with all these vulnerabilities in practice, the good news is that there have been a lot of defenses, empirical defenses developed against such attacks. For instance, they can be categorized as different detection, prevention, etc. But the bad news is that actually there is a famous security cat and mouse game, and here almost all the empirical defenses here have been attacked again by new adaptive attackers. So we can have new attack and new defense and new attack again. That means we do need certain certification for the model robustness so that we can have some guarantees and we don't need to worry about potential future attacks in this cat and mouse game. Yeah, let me know if you have questions. So this means on the high level, what certified robustness mean, right? So basically, on the very high level, it means that we do want to give a lower bound of model accuracy under certain attack constraints. For example, attack radius is bounded by something, etc., right? And slightly more formally, we want to give a lower bound of this 1 minus min-max loss. And here, the loss delta itself can represent different types of adversarial transformation. It can be additive noise, it can be semantic transformation, such as rotation and other things. And the perturbation need to be bounded, say as a like constraint C, which constrains the adversary cost budget. And then we minimize the model over model parameter theta against this worst case attack. And then we find the worst case loss. And then 1 minus the upper bound of the loss give us a lower bound of the model accuracy, which means that given a model, given a set of test data, and if we tell you that the accuracy lower bound or the certified robustness is 90%, given say L2 norm bounded by 0.3 for the adversarial constraint here, then we know there is no future attack. No matter how you generate attack algorithms, you cannot attack this model to have lower, like accuracy lower than 90%. That's the guarantee we can get. And intuitively, it means that given a decision boundary like this, each color represents a class, and we want to find, say, a radius, certification radius, such that the prediction within this radius is safe, is consistent. That's intuition. And given this certified robustness, it's very nice, and it gives us some nice properties and guarantees. And the good thing is that there have been a lot of approaches to provide different certification, basically to solve this min-max problem. As you can see, directly solving it for neural network, which is non-convex and non-concave, is NP-complete. So there are different branches of method to provide certification. For instance, given this X as an instance and assume this region or this radius here is the adversarial perturbation region, and then the first branch, as you can imagine, is we can use different linear constraints to categorize this region so that we can solve expensive linear programming or mixed integer linear programming using existing solvers. So this is, as we mentioned, NP-complete problem, and it's very expensive to solve. And currently, this branch can only scale up to 200 or 300 neurons, which is relatively expensive and not as scale as the neural networks that we are using currently. And second thing, to make it more scalable, we'll trade off some completeness of verification, meaning that we can draw a ball over this weird irregular shape, right? So that we may have some false positives, but it's fine as long as we don't have false negative. That's our incompleteness mean, right? And then in this regular ball, we can do more relaxation, like some linear, nonlinear relaxation, and it can be more scalable to provide certification. And in the end, we can even provide probabilistic certification by sample things within this ball, so that this branch is the most scalable certification recently. And as you can see, the detail here doesn't matter because there are a lot of methods, but the 3 branch is currently the state of art, or currently summarize all the existing certified robustness approaches. And they have their corresponding robust training approach to improve the lower bound of the certification. And there are a lot of details here, but I want to emphasize, mention that we do have a unified toolbox here, which is open source and everyone can use to easily implement all the certification approaches or robust training approaches, so that you can easily compare with your own method or calculate the certification for your own models to evaluate your model, which hopefully it can be useful. And the link is here. So from here, we can see it's great. The certification itself is rigorous, it's nice. But on the other hand, we can see it's expensive and sometimes provide a loose certification bound in many cases. So let's
sure. Can I ask you a very, very short question? Here we are talking mostly about the direct task when we have some constraints, adversarial constraints, and we would like to understand what is the lower bound for classification of the task. But what about inverse task when we have when we can allow for us some drop of quality, we can understand what could be the lower bound, but we would like to understand what are the adversarial constraints in this, what this lower bounds could be. Is there any research in this domain? So
I see. So currently, the most research work on the constraint as, say, if it's an image, it's LP norm, bounded image perturbation radius. Say you can add so much, up to LP norm something. And we do, in our group, we generalize such constraint to semantic transformation. For example, if you have image or whatever as a vision input and your rotation and some other semantic translation, for example, colorization, other construction, contrast, and also some other combinations of those different semantic transformation. So we provide the first work to also relax the constraint to be semantic transformation and then provide the lower bound. And in terms of this classification problem, as you mentioned before, we do have lower bound for reinforcement learning as well, which is the lower bound of reward of reinforcement learning. And the constraint of that is still the LP norm bound of the state input as a perturbation as input.
Yeah, probably I'm just asking more about this task that you're talking about right now. This is when we have this constant C. Yes, and we would like to understand what could be the lower bound depending on this constant C. But what is if we have the opposite one? We know, for example, this drop of quality delta that we can allow for lower bound, but we would like to see what could be. We would like to understand what could be the C constant in this case.
Yeah, exactly. That is definitely that is exactly doable because this is a constraint optimization. So when we calculate this C, actually usually we calculate the C directly. So basically, when we solve this min-max problem, we will be able to the output will be able to given a C, and then when we calculate the robust accuracy, we count, given so many tested data, how many data have the C, because the C is also data dependent. If you have a very bad data point, then your certification is very bad, right? So basically we calculate for each data point whether it can satisfy the C is within this constraint or outside the constraint. So in short, yes, by solving this problem, we can calculate the C as an output for the constraint. Yes.
Okay, thank you.
Yeah, thank you. Yeah, that's a good question. Even for semantic transformation, we can calculate the radius. But unfortunately, the radius currently with the purely data-driven models is not that large. So we will discuss later about other approach to further improve the radius. Yes. So let's take a look at the state of art of certified robustness. Very interesting, I feel. So certified robustness started in 2018, actually, for neural networks. And then you can see the lines, the top two lines are for MNIST on the different radius, and the middle two are for CIFAR on the different radius, and the bottom is ImageNet. And you can see over the years, there's almost a bottleneck that after 2019, there's no improvement of the certified robustness anymore, and it's almost flat, which means we do need some paradigm shift to further improve the certified robustness for neural networks. Right. So our group still maintains the state of art of some work here, but I'm not too proud of it because I think the certified robustness here still far away from being very useful from the number you can see. So with that, it means that purely data-driven models, as we mentioned before, like in single neural network, people have tried a lot of things like robust training, adding adversarial training, adding unlabeled data, adding regularization, adding ensemble model, all kinds of approaches. Still, it has reached a bottleneck. So we really need to move to another paradigm. For example, integrating domain knowledge and logical reasoning to the models, right? Why that is so important? So take the stop sign as an example we mentioned before. As a human, what do we do, right? So we usually recognize, okay, there is an octagon shape, and we see there is a pattern stop in it, and we see the sign is mostly red, and some useless information such as the stickers here, right? As a human, we can do a very good job in terms of the main task. Say, okay, this is still a stop sign, even with the useless stickers on it, but based on the extraordinary information and the knowledge. But unfortunately, as machine learning models, somehow it will be focusing on the stickers and make mistakes. So we do hope that the idea is that we can integrate, just as we shown before, such data-driven models which have good representation power and the knowledge of reasoning just as human together to ensure both high accuracy and the certified robustness. So that's our goal here. Right, and on the very high level, what it will look like, right? Basically, given a raw data, and we can optimize a model over it, and this is typically what we do in the data-driven learning. And then we know in real world there are a lot of knowledge which can encode logical relationships and the reasoning, etc. And we call it this knowledge-enabled logical reasoning part. And in this end-to-end framework, we call first part learning and second part reasoning. And our goal is to integrate the second part reasoning into the existing data-driven learning component to improve robustness or certify robustness. And take a simple example of stop sign, for example, here. So on the in the learning component, taking the stop sign as an input, we can train multiple models in the learning component. For example, one main model predict whether the input is like what type of sign it is, and later on we have multiple knowledge model predict, say, whether it's a stop octagon shape, whether it has red pattern, whether it has stop sign in it, etc. And then we have some real world knowledge, of course. For instance, a stop sign should be of octagon shape, right? And then we can map the knowledge into a first order logics like here, and use structures to connect them together and make this end-to-end inference. And then we'll discuss how we can integrate them together. But on the very high level, we can see if we give this row sign into a single model, for example, here, because of the uncertainty and the instability of the model, we can see the confidence prediction range is relatively large. And then the certification is very hard to be tight. But with a reasoning component to help correct the incorrect prediction of the learning component, we can see the confidence of the prediction is largely improved, and we can provide a better or tighter certification. So that's the intuition. And then to abstract this simple example to an end-to-end framework, we'll have this. So basically, we'll have this learning and reasoning framework, as we mentioned. And in the learning part, we can have several models, statistical data-driven model. For example, it could be neural network, it could be SVM, it could be logistic regression, whatever we like. And in the reasoning component, we can map our first-order logical rules into certain probabilistic graphical models, probabilistic circuit, and probabilistic language, etc. And then in this way, with this end-to-end framework, we can see intuitively, in terms of robustness, it is very hard to attack, right? Because, for instance, here, if we want to attack this framework, we need to attack all the neural networks, for example, in the learning component, and make sure their final adversary output satisfy the logical relationship, right? Which is relatively challenging, actually quite challenging. And there's additional several key advantages of such a component or framework, which is, for instance, in the data, because we preserve the data-driven learning component, we can leverage the powerful representation of it to learn effective models. And the reasoning component can help to encode domain knowledge, support reasoning, and correct certain incorrect predictions of the learning component. And one key advantage that I really like is that here, the reasoning component, although we need some real world knowledge, right? But compared with traditional symbolic AI, we can see that in traditional symbolic AI, we need comprehensive knowledge to make inference, right? But here, because the reasoning component, we are not using it for inference. We just kind of use it for violation check, right? So here we don't need comprehensive knowledge, which means even we don't have comprehensive knowledge, like we have useless knowledge, then our performance of the whole framework will be at least as good as a neural network. But if we have the reasoning component, if it's useful, integrate some useful knowledge which can be validated or things, then it will only improve the performance of the neural network component, which means it will never hurt the performance.
Professor, yeah, we have also the second question. Yeah, let me start, and then Ramesh also can ask a question. Yeah, my question is, what do you think? What is the main component here, like learning or reasoning? Just because it seems like when we have multiple sources of knowledge, like the starting, I don't know, points in this reasoning, just it seems like it reminds me of ensemble learning. Probably like the main advantage of this approach is just because we are learning multiple neural nets with multiple objectives, and that's why it's hard to break. Probably the reasoning could be very simple, and the main strengths could be coming from the ensemble learning. What do you think?
Oh, I see. So yeah, I will have a later result to compare with ensemble. So it's different with ensemble in the sense that similar in the sense it has several neural networks, but first of all, the neural network govern different types of tasks. So that's different because in ensemble, every neural network doing similar thing, right? And second of all, the reasoning component is very important here. In ensemble, you don't have a reasoning, so it's still a purely data-driven model, no matter how many base model we have within ensemble. But here, because of the reasoning, it enables the framework to have the logical reasoning capability. That is the most important part, I would say.
I see. But if we have the ability, for example, to fool this multitask learned ensemble, then we can also fool the reasoning part, right?
The reasoning is stabilized. For example, a row sign should be of octagon shape. This thing should always be there. So the reasoning encode some invariance, rules or invariant properties there. So the thing is that you cannot violate those rules unless you attack the neural network or learning component such that the output still satisfy the knowledge rules. That's the thing. Because if we just randomly attack every neural networks, it's with high probability it will not satisfy the logical rules, right? Because the logical rule is very specific.
I see. So inside this reasoning, we also incorporate some sort of correlation that is usually when you're, for example, fooling one DNN, also the way of how you're fooling another DNN could be correlated. And this,
Yeah, exactly. So if you fool like a stop sign to be like a speed limit sign, but the octagon shape doesn't fool, or octagon shape somehow fool to be rectangle, to be a triangle or something, then it still doesn't satisfy the rule. So the probability to satisfy rule is actually very low based on the assignment. Yeah.
Correlated multitasking. Yeah, I got it. Yeah, Dharmesh, could you please ask also the question?
Yeah, I have a question regarding the size of the knowledge base and how it scales. And what is it basically like scaling with? Is it scaling with the number of DNNs in the network, or like what is it scaling on? I guess how big the knowledge base needs to be, and how does it affect bound if we change that?
I see. Yeah, that's a good question. Indeed, here for the knowledge base, it's just actually this the third key advantage we mentioned here. So the first of all, we don't need a comprehensive knowledge base because here we don't rely on knowledge base to do inference. We only leverage it for violation check. So if we have some key knowledge rule, for example, some very important like stop sign should be octagon shape and stop pattern indicates also such things like this is enough to trigger the violation. And in terms of the scaling of it, we can flexibly use a large like a knowledge base or smaller knowledge base. The computation efficiency will not scale up with the the size of knowledge graph itself, because it's mainly the complexity rely on the complexity of the probabilistic graphical model itself. So we can easily have a later work showing that we can easily map a PGM to a GCN, for example. Then you will have a large GCN, and no matter how large your knowledge structure is, your inference time is always efficient. So that becomes efficient. Yeah.
I see. I'm trying to intuitively map, like, so in case of the example of stop sign, right? Like the octagonal shape, for example, is important as something has some knowledge value. And for example, the color being has a different value of knowledge.
Yes.
So do we have to, like, I'm trying to figure out how much each of that adds, for example, and how can we like be sure that this is enough? Like I can add like very simple thing like, if, the stop sign always are at intersection, for example. Like it's not a strong knowledge.
Yeah.
Adds some value, but how does it compare to say octagonal shape knowledge?
Exactly. Yeah, that's a good question. Indeed. So for the knowledge rules here, we also need to train it later on for this part. And when we train it, we'll give the weights to each knowledge rules automatically. And then you will see, to answer the question, with higher weights, it indicates that this rule is more important. And with lower weights, it means it's less important. And another question based on what you ask is actually how we identify robust knowledge versus non-robust knowledge, which is actually very interesting future work we are working on currently, which means we do have a lot of knowledge in real world, but some knowledge are not that useful for robustness. For example, a stop sign belongs to a road sign, right? This is very generic. It's almost useless, right? But the stop sign, if often shape, it will be very useful. So how we identify those, which piece of knowledge is more robust and how we filter it, that's actually very interesting future work we are working on currently. And there is no research on that yet, although there are a lot of research talking about how we integrate knowledge from foundation model, from knowledge graph, and all the things. Lots of research on knowledge, but there's no research on robustness of knowledge, and that's actually, it's very interesting. And the intuition of that is that you can leverage some unique properties of graph. For example, the more unique the connection it is, usually it's more useful in terms of robustness, right? More common connections are not that useful. And some coding theory can be used to identify or measure the robustness of knowledge for filtering as well. Yeah.
I see. That makes sense. I think the fact that the reasoning components are understandable component rather than neural net is aiding that. Okay. Yeah, that makes sense.
Yeah, exactly. That's the point. Yeah, thank you so much. Okay. Yeah, the here I really like, I think this is very important. Like whenever we talk about knowledge, people get anxious about, oh, what if we need a lot of knowledge and we don't have a lot of knowledge or very expensive? And indeed here it's actually a component outside and it doesn't need comprehensive because inference doesn't rely on it. I think that's very important, very helpful. And it can provide end-to-end prediction. We don't need any human intervention in the middle. It will just give you the end output. And it can provide robustness certification, I will mention later. And as a byproduct, it actually provides some explanations based on, say, which rule is violated, and we can go back to look and know which model is attacked, etc. So there is some byproduct as explanation. So interesting with this framework, I can quickly mention there are a lot of applications for it. For example, image classification, for example, NLP, and some cybersecurity tasks, etc. And like even for generative models, I will introduce later. And some safe autonomy for vehicles, for air. We do have a NASA project for like air flights, etc. So basically, I will go through some of the applications later, but before that, let's dig into some fundamental questions or research questions of this framework so we get more fundamental understanding of it, because I know everyone here are interested in certified robustness, and then we can take a look at the application later. So here with this framework, we do have at least 3 research questions we want to ask. First is how we can certify the end-to-end robustness for this framework, right? And second is whether we can prove this framework is indeed more robust than a single neural network model or whatever, right? And the quick answer for the first is also simple. Like basically, as we know before, we can provide robustness certification for, say, a neural network, which can be used for the learning component. And then the main question is how we can solve the min-max problem of the reasoning, like a probabilistic graphical model. So we'll try to show how we can approximate the upper lower bound of the min-max for the reasoning component, and then we can connect them and have an end-to-end certification. And for the second question, we can exactly show and prove that as long as the knowledge models make non-trivial contribution, basically non-zero contribution, then the robustness of this framework is always provably more robust than a single model, which is very helpful and help us to understand the benefit of this framework. And in the end, we want to make it scalable for diverse downstream tasks. And we can see, as we mentioned, we can adopt the like graphical convolution networks to represent the knowledge structure and then make efficient inference during inference time. So we'll take a look at the questions one by one quickly. So let's take a look at the certification part. So as we mentioned, the goal of the certification is given the input perturbation, epsilon I, for example, is bounded by something, and we want to know what's the upper lower bound of the marginal prediction of the final prediction, right? And we can also do the other way, as we mentioned, if we have the certification, we want to know how large the radius of the perturbation we can bound. That's also possible. And to have this end-to-end certification, we can see for the first part, given the input perturbation, we can first get the model prediction uncertainty of the learning component, leveraging some existing certification of neural networks, so that this uncertainty can be taken as an input to the reasoning component, and then we'll get the final certification of it. And then our main goal is the second part, like given the model output, basically the neural network output uncertainty as an input of the graphical model part, how we can provide the upper bound of the prediction of the graphical model itself. So here we can see, given before we do that, we need to instantiate this framework with a more concrete structure. For example, we use a Markov logic nets as one component for the reasoning, and we do have a result for, say, Bayesian networks or other things. But let's take Markov logic net as an example. So here in the learning component, we take input, say, the stop sign. I will use stop sign as a whole talk as an example, but we can see other example later. And then we train the main model, which predicts what sign it is, and is octagon shaped model, and is red model, etc. And then we can build an MLN program on top of it, and then each output is a predicate in MLN, and we have the weight rules. For example, stop sign indicates octagon shape, and we have different weights for the rules. And after grounding this MLN, we'll have a factor graph, and then we have two types of factors. One is the interface factor, which takes directly connect with the output of the learning component, like neural network here. And the interreal factor connect to all the other factors. And based on this, we can learn weights for the two types of factors. And the interface factor, we use logout, because you can imagine without any other rules, this logout will exactly reflect the original prediction probability of the neural network output. And the interface, interreal factors, the weights here will be learned. And our goal is to upper lower bound the marginal prediction probability. So basically here, V is a variable, and we want to, and our MLN is output, and every PI is output of the neural network. So we want to see what's the prediction probability for variable V equals to 1, which equals to the sum of partition function over V equal to 1 over sum of partition function over all the possible word, basically all the assignment you can see for this reasoning component. So this quantity itself represents the prediction probability, right? And given this prediction probability of the MLN program itself, first of all, we want to provide, like basically solve the min-max of it and provide a certification of it. And unfortunately, in terms of the complexity, we can see this certification problem itself is Sharpie complete because we can reduce the counting problem to it easily. And then the question is, now the certification is like Sharpie complete. Can we instead solve the upper lower bound for the robustness of this min-max problem? So here, remember our goal is that we want to approximate the upper lower bound of this like MLN output prediction probability. And the goal is to compute what if the input like a PI as the output of like neural networks, right, have certain uncertainty which is bounded by epsilon I, like epsilon of I is bounded by C, for example here. What's the upper lower bound of this final output prediction probability? So we can see the good news is that we can exactly approximate upper lower bound of this by taking a log, and it equals to max z tilde minus the mean z tilde, or like the lower bound is mean minus max over this z tilde, and this z tilde equals to the ground truth output plus some Lagrangian coefficient multiply the uncertainty epsilon itself. So this is upper lower bound. Actually, we can exactly prove it in a theorem by taking the Lagrangian conditions there. And the good news is that for this upper lower bound, in terms of the z tilde itself, it's either always monotonic, increasing or decreasing if the Lagrangian term lambda is larger than 0 or smaller than -1, or it's always convex if it's between this. So this is actually very nice property, given us a property that we can exactly get the upper lower bound approximation when the epsilon tilde equal to -c or c during the monotonic case, or zero gradient, use a zero gradient to solve in the convex case, which lead to efficient certification algorithm by we can sample the lambda many times and then like estimate which range the lambda is and calculate the upper lower bound. Every time it's a deterministic upper lower bound, and when we sample more and more, we'll get tighter and tighter bound itself. So this is the way that will provide certification for the MLN itself. And then let's take a look, see with such a certification, how much it will improve the certified robustness, and whether, importantly, whether it hurts the binary accuracy, which is very important, right? And here, first of all, take the stop sign as an example. We can see that we can connect the learning and the reasoning component and reasoning use MLN we mentioned before. And here, compare with this learning with reasoning with knowledge and a state-of-art vanilla, just a smoothing based certification method. Here is a smoothing parameter seated here, and the star means the best performance over each column. And we can see, first of all, very nicely when epsilon, which is the perturbation radius, equals to 0, means it's a binary accuracy. We can see this framework, in terms of binary accuracy, it's improved slightly, which means there is no trade-off between binary accuracy and robustness anymore. As we always know, there is a robustness and the accuracy trade-off, right? And here with this knowledge integration, there's no trade-off, which is very nice and important. And second of all, in terms of certified robustness of in every column, we can see it's significantly improved, especially on the large radius. So it's very basically, remember the figure we showed before, the improvement of certified robustness for purely data-driven models is about 2 or 3%, is like already large enough currently. But with the knowledge integration, we can see the improvement is 10% or 20%, etc., which is quite significant. And in another example, which is quite large scale compared with a stop sign example, we can see is that this is a primary net, which is a subset of image net. And then we have a lot of classes in it, for example, different ape, grade ape, and we only use 2 types of knowledge rules. One is hierarchy, which means if one model predicts it's a grade ape, and the other model must predict it's an ape because they have the hierarchy relationship, right? Or if one model predicts it's a grade ape, the other model must predict it's a non-lesser ape because of this exclusive relationship. So this is kind of answer the complexity of the knowledge before. Like here, we only need these 2 types of knowledge, which is actually very simple and can be easily get from a concept net based on the image net here. And you can see with such simple knowledge integration, similarly, we can see there's no trade-off between binary accuracy and robustness, and binary accuracy is slightly improved, but also on the large radius, the certified robustness is improved about 30%, etc., which is quite significant, and it can be applied to different downstream tasks, etc.
Professor Bo, yes. What is the last row with marked star? What does it mean?
Oh, sorry. The star means the best performance over each column, just for easy to comparison. Yeah.
Thanks.
Yeah, because sometimes the different smoothing parameter lead to different results, and we only need to look at the star rows. Yeah, and yeah, so yeah,
Also,
with that, yeah, go ahead.
Professor, we also have the question from Rushina. Yeah, Rushina.
Yes, one question I had is in the MLN or like the logical network, are the weights hand selected or are they also subject to tuning? And is there a way to trade off like your data having possible like just bad inputs or bad labels with expert knowledge?
I see. Yeah, that's a good question. So for the knowledge, we like human defined knowledge, but for the weights of the knowledge rules, we learn it. And the way we train the knowledge rule weights is that we only use benign data because the principle is that we don't consider we know any future attacks. So we only use benign data to train. And the goal for that is the benign data should satisfy the knowledge rules, and then it will help to pick the important rule with higher weight or not important with lower weight. And as you said, if the training data have some bad data point, it could hurt the knowledge rules, which that perspective we haven't explored yet. The exploration we are doing is we only consider benign data, and then in terms of bad data, it could have noisy like noisy labels or noisy features. That's fine, but there is no like adversary in the training, so that during testing we can handle all the unknown attacks, so that we don't need to do like adversary training types of thing to consider different attack during training. Yeah.
Got it. Okay, but this is still robust to noisy inputs.
Yes. Yes.
Okay. Thank you.
Yeah. Surprisingly, it's robust. I think it's mainly because of the knowledge rule. So basically, it could be, as you said, some rule maybe the weight may be not perfect, but the rule itself is important. So as long as we identify some rule, it will automatically trigger the violation. So we do explore or evaluate over different noise or things. Later I can show, and that's very interesting to see. It's very robust. Yeah. Thank you. So yeah, let me go to the second question. Basically, we want to know whether or not we can prove this framework is indeed more robust than a single neural network. So for the first question, we already show in terms of certified robustness, it's improved. But can we prove that, right? And in order to do that, we need to take a careful look at the knowledge that we used. And here, in particular, we categorize knowledge into two types. One is a permissive knowledge, which is, say, if the main model predicts it's a stop sign, then the other way, like if the knowledge model predicts there is a stop pattern in it, then the main model need to predict it's a stop sign. And the preventative knowledge means if the main model say, okay, it's a stop sign, then the knowledge model must predict its octagon shape. So you can see it's kind of like sufficient and necessary conditions between the main model and knowledge model is by the direction, right? And on the high level, the intuition is that these sufficient and necessary conditions will help you to govern the truth rate and false rate of the predictions, so that it will help you to bound the lower bound of the model accuracy. So that's the intuition. And with these two types of knowledge direction, knowledge rules, and in a simple case, we can see if the models are homogeneous, meaning they all have the same truth rate and the false rate. Here, the alpha represents the truth rate and epsilon represents the false rate. So the difference here is the larger. Then we can see the lower bound of this framework will converge to 1 exponentially fast in terms of the number of knowledge model n, which means as long as the knowledge model make non-trivial contributions, like the truth rate is slightly higher than the false rate, the more the better for the knowledge models, right? And this is intuitive and demonstrate the rationale of the framework itself. And we can take a look in a slightly more complicated case where all models have different truth rate and false rate. And first of all, we still want to show we can prove this conclusion, which is the framework itself is more robust in terms of the lower bound of accuracy than a single model, which is a main model neural network itself. And such conclusion will be held by satisfying certain constraint here. And if we take a look at the constraint, it's very intuitive actually, which means this green part actually measure similarly like the truth rate of different knowledge model K minus the false rate of different knowledge model, which means as long as they make non-trivial contributions, or the larger this quantity is, you can see the condition is easier to satisfy, and then the conclusion is easier to satisfy. And on the other hand, this alpha star represents the truth rate of the main model itself. It means if the main model is perfect, right? Main model, for example, is 100%, is a perfect model, then we can see there's no room to improve for this framework, right? Because the main model is already perfect. But you can see the point is that the knowledge will not hurt. So it will not decrease the performance. So that's a conclusion, which is very important. And we can see this framework is always robust and a single model as long as the knowledge models make non-trivial contributions, and the knowledge integration will never hurt. And with this theoretical result, we can evaluate our framework under different downstream tasks and see how effective it is. So here, this is to answer the previous question, like how many attacks we can evaluate, right? Given this framework, first of all, we can consider white box attack to attack all the neural networks here directly, for example, and we can consider black box model attack to use train a surrogate model, leverage the input and output of the neural networks, and then attack this surrogate model. Or we do a black box framework attack to train a surrogate model of this end-to-end framework and attack it. And we can evaluate against the physical attack and some unforeseen attack, which is the one you mentioned, like there could be Gaussian noise, like a JPEG or any brightness different transformations. And note that here we only train the framework under the given benign data set, that's all, and then test it over all the attacks here. We don't actually train the model given any attack here. We don't know any attack, assume. And then similarly, in terms of the benign performance, you can see it's slightly improved, which is nice. And here, in terms of the robustness against different attacks, so here the x-axis shows all the attacks we mentioned before, like a white box, like a black box, or the uncommon attack or things. And with the bar, we can see it's always improved, and it's attack agnostic, which is very nice. And with this, we can see this overall framework is quite robust and with a high certified robustness. And in the end, we can see how we can make it scalable for different downstream tasks. So basically, the idea is that, as we can see, certified robustness of ML is sharply hard, as we saw before, and we really want to make it scalable by using GCN to encode the knowledge. For instance, here, given still this stop sign as an example, we can build up a graph structure where each node represents each neural network or learning component here. And the two nodes will have a connection if there is a knowledge relationship between each other. And then we can use variational EM, say in the E step, we train the model weights by fixing the knowledge rule weights. And in the M step, we train the model like rule weights basically based on the model weights. And you can see over the training of the based on the benign data, as you can see, the important rule weights gets improved, and the not very important rule usually gets decreased or things, depends on the data. And then with this framework efficiently, it can be used for different downstream tasks as we promised before. And here I want to show a quick example that this is another scalable example of animal classification, and it has different knowledge rules. Say if it's a panda, it should be furry. If it's dolphin, it should be flipper. It has to have flippers, etc. And then we can see over different radius and compare with state-of-art certification method, it's always significantly more robust. And here the swing is a state-of-art ensemble model for certified robustness. And we can see compared with it, it's indeed significantly improved, which means the knowledge logical integration itself is actually very important. And not only this, but also there could be an NLP task where we collect all the the stock price of the top 10 tech companies, and the task is the knowledge the information extraction, like what's the stock price today, what's the stock price gain based on the NLP, and then the knowledge rule we use is as simple as just the arithmetic rule, like the stock price yesterday adds up the change should equal to the stock price today, is like that. And here you can see similarly, not only the benign accuracy, but certified robustness is significantly improved. And in the end, I want to show one example that not only classification task, but also generative model. So basically here, we integrate knowledge to a generative model in a tree structure to generate safety critical traffic scenarios for testing. And we can see if we put this prompt to a diffusion model, and you can get something like this, which looks realistic, high resolution, everything is good, but it's not true in practice, right? So basically, because the model doesn't know the real physical laws and the physical constraints. So for example, the tree knowledge, we separate them as the car in the same lane should drive in the same direction, and between cars there should be certain distances, etc. So basically, the physical rules can be integrated explicitly to guide the generative model. And similarly, we also explore some causal relationships. Say if it's a pedestrian coming out, what's the speed will cause the car to hit the pedestrian, etc., and integrate such causal relationship into the knowledge, into the generation to generate the safety critical scenarios. And there are a lot of such examples later. And in the end, I do want to mention some platforms we have maybe helpful for everyone. Like here is a unified toolkit for certified robustness. If you are interested in certified robustness, can be used. And this platform provides the framework for lower bound of reward certification for reinforcement learning against both training and testing time adversaries. And this is framework for NLP and for federated learning, for AI ethics, and another one for safety critical scenario generation for autonomous vehicles. We do have a large platform, SafeBench, hosting more than 5,000 safety critical scenarios for testing. And I want to show quick example here that with this framework, you can provide certification for semantic transformation, like we mentioned before, like if a car is rotated or it's like have different distances, sending to a sensor fusion model, we can provide certification for it. And here we can even leverage large language model, for example, ChatGPT here, because everyone use ChatGPT currently, right? And we can explore its basic properties. Say, please give me 2 or 10 safety critical scenario at the intersection of things, and it will give you description based on the knowledge base that they have, right? And then we train a retrieval database to map the NLP to each function class, and then we'll automatically generate the code which can generate the scenario in color, and then this will be end-to-end, like we just manually human ask a question, and then eventually you will automatically get some scenarios in color that you can run, which is the safety critical scenarios, etc. And I do want to mention in the last thing that we have a computation. Oh, so this is so that's a link here. We have a CVPR workshop this year, and we do have a computation for SafeBench for safety critical scenario generation. So we have perception attack against autonomous vehicles, and the defense and the planning attack basically generate different the adversarial scenarios and test against it in the SafeBench I mentioned before in this SafeBench platform. So I think everyone here is expert in autonomous vehicles, and if you are interested in the like computation, please let me know. I think it's great that we can work together to do the computation analysis. Yeah, thank you, everyone. Happy to take questions.
Yeah, thank you, Professor Bo. It seems like you have 1 minute.
Yeah, we can take a question. Yeah, sorry, I have to have another meeting.
Like, what do you think? How do we really need like the explicit certification for autonomous driving, or we can mitigate it by different means?
You mean whether we can have explicit certification for autonomous vehicles? Yes, we can. I mean, here, for example, the reinforcement learning part, right? Reinforcement learning part is exactly the certification that we plan to we give for autonomous vehicles, and the next step is how we can connect the perception, prediction, and planning together to give the certification. Now we give certification for end-to-end reinforcement learning framework, and if we have a pipeline, whether we can give a more relaxed certification against the different safety constraints or things. Yeah, that's a next step.
So you mean even for example, for production like end-to-end like autonomous stack where it could have like multiple models like prediction, planning, like ILKR and blah blah blah.
Exactly.
So we still can do a reasonable certification, not like providing like a very loose
Yes.
bounds, etc.
Exactly. We have several ongoing work on that. For example, robustness is one goal, right? But in terms of autonomous driving, there are specific goals like not collision, not hit human, all those constraints. So if we only focus on those constraints, actually the certification will become more practical and also allow larger radius to tolerate because your certification goal is more specific. Yeah.
Yep. That's nice. Okay, so let's thank Professor.
Yeah. Thank you, everyone. Yeah.
Was-
Look forward to
nice.
discuss more. Yeah.
Look
Thank
forward
you.
as well. Yeah.
Yeah.
Right.
Thank
See you.
you. Yeah. See you. Bye.